This is Astronomy 101. This recording is on the celestial motion of the stars and the seasons. Okay, let me start the program. Okay, section is called the motion of the stars, and it's appropriately pictured here in this photograph taken from Jeff Fennell near Crater Lake, Oregon. And what he's showing is the motion of the stars. He's basically taking a picture, time-lapse picture of the region around the North Star. There is Polaris right here. And you'll notice that all the other stars are moving in a counterclockwise fashion around the North Star. Now you can actually see this, go outside and see this, but you'll have to wait several hours in order for it to take effect. But this time-lapse photo is rather good. Okay, so the key ideas on daily and annual motion is the daily motion is a reflection of the Earth's daily rotation. And let me scare you a little bit with the fact that the rotation of the Earth is from west to east. This is a little contradictory to what you actually see. The other thing we'll show is what are the regions called, the region called the circumpolar region, and this we'll talk about the circumpolar stars and what they mean. The next point is the annual motion of the Earth, and it's a reflection of the Earth's orbital motion around the Sun. We will see that there is a certain path that the Sun follows in the sky called the ecliptic. And we'll talk about zodiacal constellations, which are actually the constellations that are on the path of the Sun, the ecliptic. And we'll talk a little bit about solstices and equinoxes. So remember that the Earth is in motion, that it is both orbiting around the Sun and it is rotating about its axis. So if you were standing on a point directly above the Earth, directly on the Earth's axis, that would be the North Pole, you would actually see 0 kilometers per hour. You're not rotating because you're on the axis. On the other hand, if you are at northern latitudes, your speed on this globe is 1200 km per hour in round numbers. If you're at the equator, you will actually reach maximum speed of 1600 kilometers per hour in round numbers. You can see the actual numbers here in the diagram. And then if you're in southern latitudes, again, your speed decreases to 1200. Finally, if you're at the South Pole, it'll be 0. So there's a certain symmetry about this. Okay, so the apparent motion of the night sky, even though we are rotating, and let me just show this slide one more time, we are rotating from the west to the east. That's really contradictory to what we see in the sky. So I want you to keep that in mind. That's why I pulled back to this particular slide. We're rotating from west to east, counterclockwise. Whereas if we look at the sky at night, and I'll just let this movie go, you can actually see the stars are rising in the east and setting in the west. So stars rise in the east and set in the west, but not exactly in the east or west. Some of them are actually southwest, some of them are northwest, and then some are directly west. So the apparent motion, the other thing is there is an apparent motion, and this is in one particular region of the sky called the circumpolar region. In this region, everything is rotating around this star here, which we call Polaris. So I'll just show that. So here's where everything gets a little strange, because this is the axis, the apparent axis of the rotation in our sky, at northern latitudes. So again, everything is rotating around Polaris. These stars neither rise nor set. They just circle around and circle around and circle around. You can see certain constellations. This is the Big Dipper. This one's Draco, Cepheus. But those constellations never rise, never set. They are called circumpolar objects, or circumpolar constellations. We'll talk a little bit more about that in just a moment. Daily motion. Objects in the sky appear to rise in the east and set in the west, as we've already said. The apparent motion is the reflection of the Earth's rotation about its axis. Earth rotates once a day for 24 hours. The sense of rotation is, and I have to correct this in the slide, is westward, according to looking out off the planet. However, we see it. The sense of rotation that we see is eastward. Facing north, the rotation is towards the right, and it's counterclockwise, and you can check that on Stellarium or your favorite planetarium program. So the apparent paths of the stars depend upon where you're located on the Earth. So, for example, if I am standing on an island at the equator, I will not see the North Celestial Pole, and everything rises in the east and sets in the west. And there's one point here, which I'm going to call the celestial equator, and I'll show you that in just a few moments. This line is directly at the highest point. So the equator will be at your zenith if you're looking from a local coordinate system. If I am at the North Pole, I will never see the celestial equator, but I will see the North Celestial Pole, so I'll see Polaris directly at zenith, and I will see the stars moving again counterclockwise, but nothing rises or sets. It all seems to move counterclockwise with the rotation of the Earth. At northern latitudes, as you can see, the North Celestial Pole is at a certain angle with respect to your horizon. That angle is going to be dependent upon your latitude. So for us, it is about 40 degrees, 39 degrees, and this region here is going to be called the circumpolar region. Now you can calculate that, or you can actually figure out what that is very easily. It is just the circumpolar region is at sky coordinates 90 minus your latitude. So for example, for us, this will be about 50 degrees. So any stars above this, here will be circumpolar. Any stars below 50 degrees will rise in the east and set in the west. So here again is another image for that. You'll notice these guys will be up for more than 12 hours. These guys will never set. This is about 50 degrees for us. For these stars and these constellations, they'll be up for more than 12 hours. And for those constellations that are close to the celestial equator, they will be above the horizon for 12 hours exactly. And stars and constellations that are here will be up for less than 12 hours. And then, of course, some of the southern stars will never rise. This region, again, is called the circumpolar region. It is a region above the sky that is circling around the North Celestial Pole. So just a quick quiz, and here's my suggestion in dealing with the quick quizzes in order to make things more efficient. Whenever you see a quick quiz, stop the recording. You have that ability to do so. And then answer the question in your own mind. Then go ahead and start the recording again to see what the answer is. So the first quick quiz here is: in winter, the axis of the Earth points towards the star Polaris. In spring, does the axis also point towards Polaris? Does it point towards Vega? Or does it point towards the sun? Take a couple minutes, stop the recording, and go ahead and answer this question in your own mind. Okay, so now I'm going to give you the answer. The answer is that the axis does not change at all. So if it's pointing towards the star Polaris in winter, it is also pointing towards the axis in the spring. So it does not change. The axis is always, with provisos, with caveats, going to point towards Polaris. Okay. So here again is another version of the circumpolar region, and I'll just do it very quickly and let this rotate through. And again, you can see these constellations such as Ursa Major, the Big Dipper, Draco, Cepheus. These are all what are considered circumpolar constellations. Okay, so another quick quiz. The North Celestial Pole is 35 degrees above your northern horizon. This tells you that A, your latitude is 35 degrees north, B, you're at longitude 35 degrees east, or C, it is the winter solstice. Take a couple minutes, stop the recording, go ahead and answer the question in your own mind, and then start the recording again. Okay, if you said that you are at 35 degrees latitude, you would be correct. The angular distance from the horizon to the North Star will be a reflection of your latitude. So for us, the North Star will always be about 40 degrees above the northern horizon. Okay. So now we turn to the motion of the sun. We are told as little kids that the sun rises in the east and sets in the west. This is true to some degree, but there's actually some caveats to that. So over the course of the year, the sun appears to move a little towards the east each day as seen with respect to the background stars. Now, this type of motion is called sidereal, and we'll talk about that as we get into the history of astronomy. But I want you to keep that in mind, in the back of your head. It's a very important concept and will be used later on to determine the actual periods of the planets as they move in our sky. So this sidereal motion with respect to the background stars is demonstrated very nicely in this video. It is a little less than 1 degree per day. So let's go ahead and do this, and this is a video showing the actual motion of the sun at sunrise, and you can see that it is in the southeast right now. There's a significance to that we will talk about in a few slides down the road. Now notice also that it's drifting with respect to these constellations. Notice also that it is actually moving towards the east. It started here, now it's over here. And as we let the recording go, and this is a step recording, I use Starry Night to do this, you'll notice that it's ultimately drifting away from the east and it's heading north. But the thing I really want you to see is the motion with respect to these constellations here. These constellations will have a special name, and we'll talk about that, called the zodiac constellation. There's Cancer right now. And as we continue on, notice the date, pay attention to that as well, that it's moving back to the southeast. So it moved north for a time, and now it's moving back southeast. And we'll pick up, this is a year recording, so this is 1 year in the motion. And what do I mean by that? It means that we're talking about when the sun actually moves back into the constellation that you started from. So if the sun actually starts out at Capricorn, how long does it take for it to go back to Capricorn? It moves less than 1 degree per day. So it moves roughly 365 degrees, so it's actually going to overshoot the constellation that it starts at. So this path that the sun moves on is called the ecliptic. And it is the apparent path, as the slide states, it's the apparent path of the sun relative to the stars. It is a great circle projected onto the celestial sphere. And you'll notice that it is tilted 23 degrees. At maximum, it is tilted 23 degrees with respect to the celestial equator. This has significance, as you can see from the different labels on the diagram. And I'll just grab a pen. So when the sun is at its maximum north, so this, of course, is north, so the sun is moving to the north this way. Then it is called, for our latitudes, the summer solstice. It is at plus 23.5 degrees. See if I can draw that. 23.5. Above the celestial equator, 23 degrees above the celestial equator. As the year rolls on, the sun starts moving southward. So here it's at its maximum. If I look anywhere here, it's moving towards the north. So it's moving this way. And you saw that in the movie that I did. When it's over here, it's actually moving southward. So it will ultimately reach this second point on the diagram, which I'm going to call the autumnal equinox. And you can see that this, if this is the west, this will be east. And then it moves along this path a little further till it reaches this other point, which is 23 degrees below the celestial equator. This is the negative 23.5 degrees below, so it's below the celestial equator, the celestial equator being 0. We call this point the winter solstice. It's when the sun is at its maximum southern declination. Now I should demonstrate that to you. So let me go ahead and get out of the slideshow for just a moment. I am going to launch my Starry Night program. And I want you to see this firsthand, not just the videos. The videos are great, but let's do it this way. So I'm going to blow this up, and let's hide the daylight for the time being. We really don't need it. Hide daylight. And I'm going to turn on a couple of things. View. these. I'm going to show those, and I'm also going to show the equator, celestial equator. Here we are. And I will also show the ecliptic. So here we are. Let me reset the date to 21st of December. So this is December 21st, 2018. You'll notice that the ecliptic, I'll just do a little drawing here. I hit the wrong button. That's one of the dangers of playing around with this stuff live. So let me put my guide back. Celestial equator and the ecliptic. There we go. So you can see, and I'll just change this to an angular separation. If I draw a line directly from the sun to the celestial equator, you can see that the sun is at 10 minutes and 46 seconds below the celestial equator. So this would be negative. Fast forward to March. Oh, one last thing I want you to see. Notice that the sun is, if I face east, that the sun will rise at that particular time. Let's go to sunrise. Okay, so there's sunrise. And you can see that angular separation. I'll just move the time just a tiny bit so you can see the sun above the horizon. There we go. So there, the sun is at rising in the southeast, and I'm trying to make sure that I pick the sun because I want to actually stay on it. So I'm going to center here. So here's my center. Now let's go out to March. And I'll change the time to sunrise again so that you can see that. Sunrise. I'll need to move the clock a tiny bit so that we get that going. There. 7:02 a.m., March 21st. The sun is directly on the celestial equator. Now we can figure out where exactly that is. Just I'll click on this and I'll show information and go to position in the sky. Declination is 0. And I want you to pay attention to that. That's going to show up again when you do those labs. Let me go back to December one more time. December, and then sunrise. And again, I'll just pull it up a tiny little bit so that you can actually see the sun. And let's see if we can't pull some information. Here we go. Here's the sun. And now let me go ahead and pull the information again on the sun. And position in the sky. Here, declination minus 23 degrees 26.220 minutes. Pay close attention to that. So in December, the declination is minus 23. In March, it was 0. Let's now advance to June. We already did March. And again, you saw that the sun was directly on the celestial equator. 0 degrees declination. The other side of this, let's go to June. There we go, June. Here we go. And I'll just leave it alone and leave it where it is. If I drew an angle to take a look at the angle between the sun and the celestial equator, it is 23 degrees, 10 minutes, 41 seconds on June 21st. If we pull the information on the sun, and I take a look at the position in the sky, declination 23 degrees. So we have in December, it was minus 23 degrees. In March, it was 0 degrees. And now in June, it is plus 23 degrees. Let's take a look at September. So I'll advance one more time. There, almost on the equator. Let's move the date one more time. There we go, September 23rd. So the time that the sun is on the celestial equator this year is going to be September 23rd. Not the 21st. And there's a reason for that. Show info, position in the sky, there. 0. 0 degrees declination. These 4 points will be important to us. And then if we go back to December 21st, and do the declination one more time just to be sure. There, minus 23 degrees. So the sun seems to move, and I'll just stop this, or let me quit the program or hide it. The sun seems to move this way. The declination is 23 degrees, 23.5, thereabouts. Here, at the autumnal equinox, the declination is 0. Rises directly in the east, sets directly in the west. Here, it rises in the northeast and sets in the northwest. Here, winter solstice. The sun rises in the southeast and sets in the southwest. Its declination is minus 23 degrees. And then here at the vernal equinox, the declination is again 0. So this is the annual motion of the sun, and I did this live, so I'm not going to show this. So more on the Earth's motion. The Earth's axis tilts by 23 degrees, which means it'll keep pointing to 23 degrees, 23.5. It'll keep pointing towards Polaris, both in the summer, the winter, the fall, and the spring. Now this has an effect on which hemisphere gets the most direct sunlight from the sun. You can see that a little tiny bit from this diagram. In this particular position, it seems that the northern hemisphere is getting the most amount of direct sunlight with not as much going on here. At this position, it's the southern hemisphere that is getting more direct sunlight, and the northern hemisphere not as much. Note also that this particular slide gives you the average speed of the orbit of the Earth around the Sun at 107,000 kilometers per hour. Seems really, really fast. There's very interesting reasons why we don't feel that. Okay, so motion along the zodiac. This is another thing that I was trying to show you, and let me just go back. I'm going to go back to my live feed of Starry Night, and let me go to today's date. Get that done. No. Okay. So I'm going to show the labels of the zodiac constellations, or these constellations that the sun appears to move through. There we go. Okay, so let's go ahead, and I'm going to move the sun on a daily basis. We already saw that the sun seems to be moving 1 degree eastward each day as it moves along its path. Now I think I'm centered, so I'm just going to go ahead and advance the clock. February 2nd. Notice that it moves through a set of constellations. Here is Pisces. Here is Aries, coming up on Aries. So now around May 15th, or let's get to June 21st. The sun is currently in the constellation of Gemini. That's here. And one question you might have is, what stars can I see? What constellations can I see at midnight? And I claim that if we were to look at midnight, we would see Sagittarius and Scorpio as the principal constellations at its maximum height. Let me, while I'm at it, show off one other thing. The meridian. There we go. So if we were to look at midnight or at noon, and let me just move it over just a tiny bit. So here is the sun at noon on June 21st, 2019. It is directly on the meridian. That is this guy. You'll notice that it's about 70 degrees, almost a little around 75 degrees above the actual horizon. If you take the difference between here and here, you would actually get, again, the 23 degrees that I advertised. And so now let's advance now to September. And as I indicated, I have to go back to 23rd. So now, at noon, the sun is just a little tiny bit past the meridian. It's in the constellation of Virgo. And I claim, well, there's a way of knowing this. If we look at the zodiac, that's what these constellations are called, the zodiac. I'll just go back to my show. these constellations that the sun is moving through are called the zodiac, and you can actually make a prediction as to what constellations you would see at midnight based on where the sun is. So if I see Leo, Virgo, and Libra at midnight, I know that the sun is in Pisces or thereabouts. If I see at midnight the constellations of Pisces and Aquarius, I will know that the sun is actually in Virgo. Now this has a significance in that I can actually also make a prediction as to what season it is. So if I see at midnight Virgo, I have a pretty good idea that the sun is in Pisces and I am in spring. If I see the constellations of Sagittarius and Scorpio, then I know that the sun is in Gemini and I know I am in summer. Okay, so as the sun moves along the ecliptic as seen from the Earth, it passes through these 12 ancient constellations known as the zodiac. Most of these constellations date from the time of the Babylonians, and they are very familiar to us from astrological lore. Are you a Gemini? That means that you get along very well with Scorpios, and so on and so forth. They can actually be used again as an astronomical calendar, as I indicated earlier on in our lecture. We see which zodiacal constellation is highest on your celestial meridian at midnight, and the sun is in the opposite constellation. You should have a diagram of the similar to this in your text. So, we have seen that the sun goes to a maximum of 23 degrees above the celestial equator around June 21st. It goes 23 degrees below the celestial equator around December 21st. And then during March and September, it is 0 angle with respect to the celestial equator. So I'm going to give these 4 positions a name. So 2 of these positions, plus or minus 23 degrees, I'm going to call solstices. The solstice is derived from the Latin word solstire, and it basically translates from the Latin to the sun stands still. This occurs, the solstice occurs when the sun is at its maximum northern and southern declination. And again, I showed you those declinations in Starry Night with particular reference to this. So when it is at plus 23.5 degrees, it's at its maximum northern declination. You are at the summer solstice. When I am at minus 23.5 degrees declination, I am at the winter solstice. So it occurs twice a year in June and December. Summer solstice, maximum northern. Winter solstice, maximum southern. The other 2 points, the points where the sun is actually on the celestial equator, I'm going to call those equinoxes, from the Latin word equinatus, meaning equal night. The equinoxes are where the sun is at 0 declination. And there's 2 points. One in March, heading north. We call that the vernal equinox. The other one, heading south, we call that the autumnal equinox. Again, the declination is 0 in both cases. They occur twice a year in March and September. Vernal equinox, sun crosses the celestial equator moving north. Autumnal equinox, a sun is crossing the celestial equator moving south. This occurs in September. Okay, so we have those 4 points that I showed you at the very beginning on the celestial equator, and I refer you back to that slide. So now, how does that affect things? Well, for one thing, it causes a change in the length of the day. So when the sun is at plus 23.5 degrees above the celestial equator, again, this summer solstice, in this diagram, as you can see, I didn't say that quite right, so let me just say it again. When the sun is at plus 23 degrees with respect to the celestial equator, that would be here. And as you can see, there is a very long path that the sun has to follow. I went the wrong way. It's a very long path that the sun has to follow to rise from the eastern horizon, pass along to the meridian, and then go down to the west. It means that the day is going to be significantly longer, roughly about 18 hours. When the sun is at the winter solstice, minus 23 degrees, then the sun has a much shorter path to travel from east to west, and we call this, again, the winter solstice. It means, for as far as time of day, here the path is short, so the sun is going to take less time to actually rise in the east and then set in the west. You actually have shorter amounts of daylight. So summer solstice, long path, long day. Winter solstice, short path, short day. And then these guys occur twice. This green line right here, and I'll just color it with my pen. This is the equinoxes. These are the two equinoxes, vernal and autumnal. And this is where the sun will have the same amount of distance to travel. So you'll have an equal amount of day and night. Now, interestingly enough, if you look at the diagram carefully, if this area right here, going along here and down, this is the southern hemisphere. And if you note that while in the northern hemisphere the path is very large for the sun, in the southern hemisphere it's very, very short. So this summer solstice for us is a winter solstice for anybody in the southern hemisphere. And symmetrically, the path is very short here during the winter solstice, so we get short days, but it's very long for our folks in the southern hemisphere, and so this will be our winter solstice here is going to be their summer solstice here. Okay, so in the summer solstice for us, long days, and for the folks in the southern hemisphere, short days. In the case of the winter solstice for us, short day for us, long day for people in the southern hemisphere. Okay, and this actually is a continuation of this diagram. I will let you read that. It's pretty much what I've already said. So, a summary of annual motions. The annual motion reflects the Earth's orbit around the sun. The ecliptic is the sun's path relative to the stars. The obliquity of the ecliptic is 23.5 degrees, so the ecliptic can be 23 degrees above the celestial equator, in which case for the northern hemisphere it's summer, for the southern hemisphere it's winter. Or it can be minus 23 degrees below the horizon, below the celestial equator, in which case it is our winter and their summer. The constellations of the zodiac are nothing more than the path, than those constellations that lie along the path of the sun, i.e. the ecliptic, and we can actually tell what season it is based on what zodiacal constellations are up and on the meridian at midnight. So if Gemini and Taurus are up at midnight, we know that the sun is in Sagittarius and Scorpio, and therefore it is winter solstice. If the constellations of Sagittarius and Scorpio are high in the sky at midnight, then we know that the sun is in Gemini and Taurus, and it goes on. The equinoxes, the sun crosses the celestial equator. There are two of them, the vernal and the autumnal, and the solstices, the sun at maximum north or south declination. The length of the day depends upon the location of the sun along the ecliptic. Okay, I'm going to stop here, and I'll do a separate recording for that.